All right, so let's get started. This lecture is about pseudorandomness, continuing from where we left off the last time. All right, okay. So the premise of this lecture is that cryptography needs randomness. Why do you need randomness? You need to pick your keys. Why do you need to pick your keys? Because you need some information that the adversary doesn't know. Okay. So if I am completely deterministic, the adversary would run me, essentially, and they would know exactly what I do. Okay, so randomness is absolutely essential. The question is, where do we get randomness? You know, several sources. You could imagine, you also try to, those of you. Where do you get randomness? In practice, you either use specialized hardware, some of you guys know this better than I do. Use noise, transistor noise, use input. You know, when you go to sort of, pick your certificate on the MIT website, it asks you to move your mouse around, generating randomness, presumably, right? So all these tricks to generate random numbers, quite often they don't generate truly random numbers, truly random bits. They generate biased bits, right? And that's, again, you know, our assumption in cryptography is that you have uniformly random IID, independent uniformly random, identically distributed bits. And if you don't have that, our security is not guaranteed. For example, think about Shannon's one-time pad, okay? And instead of a uniformly random one-time pad, you have a sequence of bits. Each one is biased to 1. Let's say 3/4 biased to 1. Now you suddenly start seeing information about the message, right? And that you want truly random bits. And if you have some source of entropy, whatever that means, I'm not going to really even formally define it here. There are ways to extract uniformly random, like real true random bits, like distill or extract true random bits from it. And there's a big area of research that studies this question itself. It's called the theory of randomness extractors. Again, this is not something that we are going to go into any level of depth here. But let me start the day with a puzzle, right? Let's all wake up, myself included. Okay, so let's say you have a sequence of bits. They're independent, but they're biased towards either 0 or 1. And you don't know what the bias is. You don't even know which way they are biased. Right? And my goal, so let's call these bits, this is von Neumann's trick. I mean, everyone in the world should know this, including you. Right? So let's say your transistor device produces a sequence of bits, B1, B2, up to Bn. And these are independent. But each one has bias P. In the sense, the probability that each Bi is 1 is some number P, which I don't know. And I want to extract bits B1 prime up to Bn prime, which are truly random. Truly random, independent, identically distributed, but truly random bits. How do I do it? This is 1940s, von Neumann came up with this trick. And this is really, if you think back, it's the beginning of randomness extractors. Yes, not you.
What if you subtracted them?
Sorry?
Subtracted them?
What do you mean, like B2 minus B1? Something like that? XOR B1, yeah, that sort of thing.
Oh yeah, I guess XOR. Yeah.
XOR,
Because then like the P's then cancel out. So like if...
Good.
No, XOR, I feel
Good.
something
Yeah, that's a good idea.
It's like they're both going to agree more than they're not going to agree. So
good. So if you XOR, if you have a, so here's a theorem. If you have a bit, if you have 2 bits, each with bias epsilon. It's a bias meaning, the probability that they're 1 is half plus epsilon, epsilon away from half. Yes. You XOR the 2 together. What's the bias? Turns out you can do the calculation as epsilon squared. Epsilon squared, because epsilon is less than 1, is smaller. Now, if you do 2, you get epsilon squared. If you do 3, you get epsilon cubed. If you do k, you get epsilon to the minus k. And when k is large, this guy is really, really negligibly close to 1. And that doesn't work. But you know what? You're only getting, in most of the class I'm happy with negligibly close to half, not now. Okay. Let's say I push the boundaries. Let's say I really want truly uniform bits, sequence of bits. How do I do it? Yes?
I mean, I don't know if you can get n of them, but I know you can like...
I don't want any of them. Yeah.
So like if you flip 2 in a row, if they're like 0, 1, that could be heads, or 1, 0 could be tails. And just ignore the other cases.
This is von Neumann strip, right? So what is the idea? You look at the first two, yeah? If it is 0, 1, output 1, let's say. Okay? If it is 1, 0, output 0. If it is anything else, don't do anything. Just skip it and go to the next sequence. Go to the next bit. Yes? So what is the idea? The probability, no matter what the bias is, assuming independence, the probability that the 2 bits turn out to be 0, 1 is the same as they turn out to be 1, 0. That's it. Right? You lose a bunch of bits here. Right? You're certainly not going to output at most n over 2 and definitely not n over 2. Right? You lose a bunch of bits, but you get perfect randomness. So there's a trade-off here. The XOR trick would give you more randomness, more bits as output, but negligibly close to a half. And this will give you less bits, but perfectly a half. Okay. So this is just the beginning. I started by assuming independence between the 2 bits. In reality, nothing is independent. My keystroke at time now plus half a second is not independent from my keystroke now. Yes. So you still want to extract, and there's a whole theory of randomness extractors, and people have worked very, very hard on it. Yes.
So when you say go to the next pair, just like you mean copy 0, 0 to the next the prime?
No.
Just like ignore them.
No. Well, just ignore them. Just ignore them, right? So I look at the first 2 bits and I say, well, if it is 0, 1, I output 1. If it's 1, 0, I output 0. If it's anything else, I say, I'm not going to output anything. I'm going to ignore these guys and move on. Okay. So you can do a lot of things. It's a rich theory of randomness extraction. It's connected to coding theory. It's connected to list decodable code. It's connected to Goldrake 11. But that's not what we do. So I'm only saying this to make the point that randomness is expensive. You never get, true randomness. You have to have a large source of, somewhat random bits to distill to a small source of random bits, and even that, who knows? So what I want, on the other hand, in cryptography, I need randomness all over the place, right? I mean, every time I encrypt, you haven't seen quite probabilistic encryption, but it turns out that every time you encrypt, you need randomness. So where do I get all this stuff? And I encrypt a lot of things, my email, okay? It's not going to, okay? Okay, so what I want is pseudorandom generators, which are deterministic programs. There's no randomness, it's deterministic. One program, one function, G, which takes a small seed, small meaning what? Like n bits, so think of n as 128, like the security parameter, and expands it into a very large polynomial length sequence of randomness. So n to the 100, okay? Possible, yeah. That's the kind of objective. And the output cannot be random. I mean, it cannot be random because I cannot create entropy out of nothing, right? But it could be good enough. It could be random enough. In what sense? For all practical purposes, I will claim that you only need you don't need true randomness. You only need to be random against the people who are observing the dice. Okay. So that's what we'll argue. Another question is, that's fantastic, right? I mean, if I have this, I can take a very small source of like very distilled random bits, like true, pure random bits, using the XOR technique or the von Neumann trick. And now I have 128 bits, okay? Now I need to expand it into 1,000,000 bits, okay? And I can use it in a cryptographic application and so forth. So the question is, what does seemingly random mean? What is good enough to, right? What is good enough? What is random enough? Okay, well, let's try, okay? So what is, so is it clear what we're trying to do? Okay, good. So how would you define pseudorandomness? How would you, yes?
Same type of thing we had for the one-way function.
Yes.
No algorithm that tries to decide between that and a true random thing.
But that's not a one-way function definition, yes? To be clear, one-way function says there is a particular task that the adversary is supposed to do. Namely, given f of x, compute x. He fails. That's what one-way function is. Yeah.
Yeah, given the pseudorandom string and the truly random string, decide which one was the.
All right. You're 10 minutes into the game. Let's back up. Okay. Let's back up. Have you seen this definition? Yes? Okay. Not really. Okay. We will get to it, but let's backtrack from there. Okay. What is a natural? I mean, if you are in the early 70s, okay, or late 70s, that's fine. What is the natural way to try to define pseudorandomness? People did, actually. People said all sorts of things like, you know, if there's a chi-squared test that you can use to measure randomness, if my sequence of bits passes the chi-squared test, you declare that it is random. Okay? But that's not good, because if it passes chi-squared test, maybe it passes chi-cubed test. Okay, I'm making it up. Okay, who knows? Yes, that kind of points to your definition. Okay, but let's get there one step at a time. So one, way to do this is to try to sort of understand what are the properties of random strings. And I want to say, a string is pseudorandom. G is a pseudorandom generator, one that generates pseudorandom strings, if it has these properties. Okay? That's kind of a natural thing to do. So what is a property? Here's a property. Yes?
Given that you've seen some n bits, you can't predict the n plus first bit.
Good. Okay. Yes? Okay. So if it's a truly random string, if I see the first 100 bits, I cannot predict the 101th bit, except probably happen. Yes. So a pseudo-random string should have the same property. Yes. For every I, the polynomial time algorithm cannot predict. Good. Okay. So I didn't say it. The important thing here is that I require that this guy who tries to predict the I plus 1th bit from the ith bit is polynomial time bounded. If he is not, he will always be able to break these kind of things, because the string is not random. I mean, there exists a bit which I can predict from the previous sequence of bits. The key thing here is that I require, so random enough is against all polynomial time adversaries. So no polynomial time algorithm can predict the ith bit given time first dimension. That's next to predictability. Here is another thing, another property of random strings. What is another property of random string? Given the 100 bits, first 100 bits, you cannot predict 101. Very good. What is another property of random strings? Yes.
Given any subset of the bits, you can't predict any other one?
You can't predict any other one. Yes, so this is just a blown up version of, this is not next bit. What is the thing about next bit? Maybe how about the previous bit? Okay, the last, the 50 bits, if I give it to you in a random sequence, you shouldn't be able to predict the previous bit. There's no ordering. Yes? That's another definition. More generally, given any subsets of bits, you shouldn't be able to predict any bit outside the set. That makes sense. What is another conceptually completely different way of property of random strings?
Given, I guess your seed and your random bit pairs, like a series of them, you can't figure out, what the next pair would be?
What do you mean? I give you a seed?
Yeah. And then you feed it into the pseudorandom generator.
Correct.
And you get, some random string out, and then you get another seed, and then you get some other string. And if you do this a lot of times, you can't figure out, given a seed, what the next thing would be.
The question is, what does it mean to figure out what the next thing would be? Okay, so hold that thought for half an hour. Okay. Here is another property of random strings. They are incompressible. Okay. Yeah. I mean, I can't compress random strings into something smaller in a way that I can recover from the something smaller. I can recover the random string. So incompressibility. Okay. So again, generator G is pseudorandom. If there is no polynomial time algorithm compressor that takes the output of the generator, compresses it to something smaller, and then another polynomial time algorithm that recovers the right? There's no compressor, polynomial time compressor, decompressor pair. Right, that's another type of So these are all English definitions. We haven't really formalized it, but we'll get to it. Right? So these are I mean, on the face of it, these guys are different notions, right? I try to formalize what it means for a pseudorandom sequence to have one property of a random sequence, another property of random sequence. These guys are completely different definitions on the face of it. Yes.
What exactly do you mean by incompressibility? Like, you can't get it to n-1 bits?
n-1 bits, correct.
Like, guaranteed? Like, couldn't you compress that one then?
No. So, the right definition has a trade-off between the amount you compress and the probability of success in recovering the... I'm not going to define this.
Okay. But, like, I don't actually know what compressing is, but, like, if I just had a bunch of ones and, like, you managed to write the number of ones.
Yeah, but what is the probability that you get a bunch of ones in a row, if you have a random string?
That I get some string of, like, some.
So you're trying to argue that a random string is compressible, in fact, but it isn't, yes?
Okay, I'll think about it.
Yeah, please. Okay, so we're not going to define it. People have defined all these things, but these are sort of specific properties of random strings that we are trying to say, well, I can translate that. But what I want is what's your name again? Arsene. What I want is to formalize all properties of random strings. Okay? All properties of random strings. So this, how would you do it? I mean, think back to the Turing Test, okay? We tried to say, what does it mean for computers to think? I don't know. I don't want to define things. It could be that a computer think if it multiplies two numbers exactly as fast as a human, okay? Or it recognizes cat pictures exactly as fast as an average human, as well as these are specific properties. Don't make any sense, okay? What you want to say is that if the computer is human-like, if no algorithm can distinguish between interacting with a computer and interacting with a human, yes? That formalizes all properties of humans, right? That's what you want. You want to formalize all properties of random sequences. And that's the indistinguishability definition, right? And that is the king of definitions. It says that there is no polynomial time algorithm that, I make the guy interact with a random sequence. In other words, I give him a random sequence of bits, or I make him interact with a pseudorandom sequence. In other words, I pick a random seed, a small random seed, compute the pseudorandom generator, feed it to this guy. He cannot distinguish which world he's in, except with negligible probability. Okay? And that says, this string is pseudorandom if it has all the properties of a random string. Okay, so this is the definition of pseudorandom. And now you say, well, why did I tell you about these two definitions if that is a definition that I really care about? So the real sort of, the beautiful thing here is that all these definitions turn out to be equivalent. It doesn't matter if you formalize one property or another property or formalize all properties, they're all the same thing. Okay, that gives you confidence that you're onto something. You're doing really the right thing. Okay, so now that said, let's actually define things. And I'm not going to talk about incompressibility here at all. I'll talk about the other. It takes a bit more time to define all these subtleties that you need to take care of. Okay? So here's indistinguishability. Okay? I'll call this the cryptographic Turing test. Here's what it says. I want to define what a pseudorandom generator is. Right? Pseudorandom generator is a deterministic polynomial computable function. Takes n bits to some m bits. M has to be bigger than n, otherwise it's not generating anything. Okay? Okay? At least n plus 1. That's correctness. Security says that for every polynomial time algorithm D is a distinguisher, it's either given the output of a pseudorandom generator. Un is the n-bit random, the random distribution on n bits. That's un. Right? So take a random seed, n-bit seed, feed it to the pseudorandom generator, get the output and give it to the distinguisher. That's experiment 1. And he outputs 0 or 1. Okay, so 1. The other experiment is take a truly random m-bit string, large string, feed it to the distinguisher. He again outputs 0 or 1. What I want is that the probability that he outputs 1 in both cases is very close. So he doesn't distinguish. Yeah. So the 1, think of it as his prediction that I live in the pseudorandom world. So it says, you know, the probability that the distinguisher says pseudorandom, he yells it out when he is given a pseudorandom string, is a probability that he yells out pseudorandom when I give it a random string. So, I mean, he's not doing very much, is he? Right? That's the definition. Yes. This is the Turing test. Okay. Very good. So this is indistinguishability. Any questions? Any questions at all? This is super important. Yes.
Why did you define it with respect to n bits?
What do you mean? I see. So, okay, good. Very good. So really what I want, and I'm not going to write it down very much, I want a sequence of functions, right? So g sub n, which I didn't write g sub n, I just wrote g, is a function that takes n bits and expands it to some n bits. I want a sequence of these functions, one for every n. But typically I'll just write just 1g. It's a lot of energy to write down family of functions. So really, what's your name again? Venkat. Is pointing out is that really what I want is I want an algorithm that takes 64 bits and goes to 64 square bits, 65 bits and goes to 65 square bits, and so on and so forth. So this is a family of functions. But typically I'll just write it as 1. And I'll instantiate n with a large enough number, so security parameter, and that'll do the trick. Okay. Good. Okay, that's indistinguishability. Yeah, it's exactly what I said. You know, you should really think about it as the two worlds, the pseudorandom world and the random world, and the guy tries to distinguish which world he is in. Can't. Next bit of predictability, that's the other definition. First definition we look at. Again, G is we have G if it expands, number 1. 2, what does it mean, next bit unpredictable? For every polynomial time predictor, probabilistic polynomial time predictor, and every number I, 1, 2, 3 of m is the output line, it is given the prefix, the I minus 1 bit prefix, the probability that it outputs the I bit, the next bit, is close to half. Minus half is negligible. Half plus minus epsilon is what you require. Yes? Good. So that's next. Now this is, how else would you formulate it? Yes.
Is this polynomial time in I?
Is polynomial time in the input line, right?
Which is I.
Which is I for every I, yes?
But then I could always give it a large enough input that it can brute force.
That's right. So you won't be able, so another way to say it is that you won't be able to construct a pseudorandom generator that stretches from n bits to 2 to the n bits. It's just impossible. Because you feed the predictor 2 to the n, come on, you have to give the guy time to look at the input, in other words, polynomial and 2 to the n. And if you give him time polynomial and 2 to the n, he'll brute force over the input and you'll distinguish. So you cannot, so corollary, you cannot expand n bits to 2 to the n bits. Not possible. In fact, you can even say, you can't expand n bits to super polynomial and n bits, if you want, so polynomial time. Good. Yeah? Very good. Very good. Very good. Okay. And these guys turn out to be equivalent. That's our first theorem. First non-trivial theorem for today. So how do I do it? How do we do it? Let's do one, one way is actually pretty trivial, and the other way is it takes work. So which way, what's your guess? Which way is trivial? Given all our discussion, I said one definition is the Turing test, and I proclaimed it from the rooftop. Of course, it has to be something special, yes? So if a PRG satisfies the indistinguishability definition, the Turing test definition, then it is next bit unpredictable. That's the easy case. Yes? How? Good.
Yeah, if we can
Very good.
predict the next bit, then we can use that to just like look at the first n-1 bit of the random string and the other one.
Yes.
And then
How does it give you a distinguisher? So you want to say, right, I mean, if there's contrapositive, if there's a predictor, next bit predictor, then there's a distinguisher.
yeah, we can, for the random string we will not be able to predict the next bit, but for the pseudorandom one we can.
Very good. Very good. Okay, so let me dig into that. Okay. All right. So suppose, again, contradict by contradiction. Okay. So this is which direction? If G satisfies indistinguishability, then it satisfies next bit unpredictability. In other words, if it doesn't satisfy the next bit unpredictability, then there is next bit predictor, right? Which given a prefix, some prefix, outputs the next bit with probability half plus 1 on the polynomial for some polynomial. Then I want to say it violates the indistinguishability definition. In other words, I want to show a distinguisher for this generator. That's a goal. Right? Okay? So instead of feeding him the output of the generator, the prefix of the output of the generator, let us feed him a random bits, I random bits. What's the chance that he'll predict I plus 1 to random bit? It's hard. Okay? I mean, he can be stupid and do it. Well, he won't be able to. He won't be able to be stupid. That's right. I mean, he'll be able to do exactly half. Yes. Even stupidity, you cannot predict less than half. Okay, so yeah. Right. So that's that. I mean, the distinguisher is the predictor. Okay. In other words, the distinguisher takes the ith prefix. Yes, the I for which this thing is guaranteed. This statement is guaranteed. He'll feed the ith prefix to the predictor. He'll see if what the predictor outputs is actually the next bit. So the distinguisher gets the entire. Yes. What is the distinguishing gain? The distinguisher gets. So this is m bits, all m bits, or the distinguisher gets m random bits. Yes. And he says, let me pick. In either case, he says. Pick, call it y, yes? y1 up to y I minus 1. Feed y1 up to y I minus 1 to the predictor. If the predictor outputs the right bit, the next bit, y1 up to yi minus 1, equals the yi. I know yi because I know all the bits. If he does the right thing, then say pseudo-random, else say random. Yes? That's that. Very easy. Yes? It should be easy to think sort of high level what's going on. The indistinguishability definition says I pass all statistical tests. Next bit is one statistical test. Okay, so if I pass all statistical tests, then I better pass the next bit entry. And incompressibility for that matter, but you didn't even define it, so. All right, so the other way around. And that's the statement with content. Okay, so let's see. All right, so if PRG is next bit unpredictable, then I want to say it is pseudo-random. In other words, suppose it's not pseudo-random. Right? Suppose there is a distinguisher that wins in this game, in the sense the probability that the output is 1 minus the probability that this guy outputs 1, the absolute value, right? Because either one could be bigger than the other. All I care about is the difference. It's bigger than 1 over 4. Say this is true. Then I want to show an next bit predictor. That is challenging if you think about it, right? Because I say, the guy passes some statistical test, and I want to say, I want him to pass this statistical test, the next bit predictor test. How do you do that? So I want to convert convert the distinguisher list to a next bit predictor threat. In other words, I want to show that the spread actually succeeds given sort of the first j output bits. it'll predict the next one correctly with half plus 1 over polynomial. That's what I want you. Okay, and this illustrates the first technique in cryptography. You use it all over the time, again and again and again and again. It's a very, very simple sort of technique, but one has to, yeah, it's the first time you see it. That's called the hybrid argument. And then we'll do, so 2 steps. All right. Okay, so you're given this. This is what you have at hand. The distinguisher algorithm, this, that does this. Yes. Epsilon is, think about it as 1 over polynomial n. Okay. So this is what it does. What I want to construct is a predictor that takes prefixes, outputs, and exits. Yes. How do I do it? Here's how I'm going to do it. Okay. Step 1, I'm not going to construct the predictor. I'm going to say something about this distinguisher, the behavior of this distinguisher. Okay. Step 1. No predictor yet. Will come in a few minutes. All right. I'm going to define what we call hybrid distributions. Okay, so what are hybrid distributions? The first hybrid distribution is the output of the pseudorandom generator itself. That's the red sequence of red bits. The second, the extreme other hybrid distribution, well, let me not do it, is the sequence of truly random bits. That's the all blue bits. And now I'm going to go from the all red to the all blue in a sequence of small steps. Okay, what is a small step? The one before this guy is all pseudorandom. I generate the output of a pseudorandom generator, m bits, remove the last bit, discard the last bit, and replace it with a truly uniform bit. Okay, that's why. This is the output of the pseudorandom generator, and this is truly random. Nothing to do with anything else. Okay? That's the first hybrid. What is the next hybrid? You know where I'm getting at. Yes? Compute the pseudorandom generator output, chop off the last 2 bits, and replace it with truly random 2 bits. Keep going this way, you will reach there in m steps. Yes? Those are the distributions. Okay. So the first thing you want us to do in a hybrid argument is to define a sequence of hybrid distributions, like so. Yes, that go from one to the other. And what is the point? You want to be able to argue. You don't want to have this huge string that looks like one thing or the other. You want to argue with small steps, tiny steps. And that's the point of defining these hybrids in the first place. Found claim. Okay. All right. I claim that since the distinguisher distinguishes between the top and the bottom with advantage, meaning the probability that the output's 1 here and 1 here is bigger than epsilon, there is some I such that the probability that the output's 1 here minus the probability that the output's 1 here, meaning what? If I generate this probability distribution, I feed it to the guy. Okay? The output's 1 with some probability. Call it P sub I. I generate this distribution, feed it to the guy. The output's 1 with some probability. Call it P sub I minus 1. The difference between P sub I and P sub I minus 1 is at least 1 over m. So. Not for all I, but there exists an I. Yes? He has to. No matter what he does, he has to. Can you tell me 2 words proof for this statement? 2 words. Beautiful. Those are the 2 words. Okay. Triangle inequality. Okay, so let me write down triangle inequality. Okay. So the probability that, let me make my life easier. We say distinguisher on input d sub 0, output 1. So this probability, I'll call this, well, d sub I, outputs 1, I'll call this probability p sub I. Okay, because I don't want to write the whole thing. So what do I know? I know that P0 minus P sub m, absolute value, is at least epsilon. Yes. Bigger than epsilon, yes? That's what I started with. But what is P0 minus P sub m? It is P0 minus P sub 1 plus P1 minus P2 plus P2 minus P3, you get where I'm going, Pm minus 1 minus P3. Telescopes. Therefore, the absolute value is at least this is triangular inequality. Yeah, I should. Yes? Maybe I should just have a. So suppose each of these guys, for contradiction, is less than epsilon over m. Should be all sorts of greater than or equal to. Suppose for contradiction, that each of these is less than epsilon over m, then the whole thing is less than epsilon, contradicting the fact that the string structure works. So, rolling it back, there has to be some I such that pi minus 1 is at least epsilon. Okay. Profound? Not really. It's pretty simple, but this is the core of a hybrid argument. Chop things into small steps, hybrids, and argue about small steps. Okay. This is the hybrid argument. So far so good? Yes? So yeah, again, define Pi to be whatever I said. P0 is the random, Pm is the pseudorandom, and the difference between the two is the difference between some two adjacent hybrids is bigger than epsilon. That's why. So what? Do you see that we have moved a little closer to being a next bit predictor? Right? I'm arguing about one bit. Okay, so now how do I design the next bit predictor? Okay, so at this point it's pretty easy. You there are a small finite number of possibilities. You juggle through it, you get yeah. So what does that top thing say? It says triangle inequality can go. Pretty safe, yeah? Maybe I'll put you first. For Randomness. Okay. So again, Pi minus 1 is greater than epsilon over m. Pi is the sequence of I is pseudorandom. And Pi minus 1 is I is random. Pseudorandom, and this is wrong. Yes? So the fact that Pi and Pi minus 1 are different, I claim means that the adversary actually predicts the next bit, ith bit given I minus 1. So how do we exactly kind of form it? How do we do the math? Yes. I could leave it as an exercise, but this one is the first one, so let me kind of do it. So here's one way to do it, by no means the only. So d sub I, again, right, the ith bit is pseudorandom, yes? Let me define an auxiliary distribution d prime, di prime, where the ith distribution, the ith bit is not random, but it's opposite of the pseudorandom, right? I generate sort of the ith bits, yeah? The ith bit, I flip it. The rest of it is random. Why am I doing it? Because of the following. Yeah, I claim that Pi minus 1 claim minus 1 is Pi plus Pi prime over to the average of Pi and Pi prime. Yeah? Does anyone see why the short explanation? How do you generate a random bit? With probability half, I output yi, whatever is the right bit. With probability half, I output the complement of yi. That is a random bit. Yes? So, essentially, if you work through math, you get this. Yes? So this is the probability that the distinguisher outputs 1 on y1, y2, y3 up to yi, and then random. This is the probability the outputs 1 on y1, y2, y3 up to yi minus 1, yi complement random. Yes. And the average of these two is sort of like you flip a coin and you pick one of these two events at random. Yes. And if you do that, you truly get ith bit is truly random. Yes. And half probability is yi, half probability is the complement of yi. It's truly random. That's this game. That's why it's there. The probability that something happens here is the average of the probabilities that. You see why? Yes or no? Clear. Okay. Conditional probabilities. Okay. Just exercise. Yeah. So the intuition again is a way to generate the distribution vi minus 1, which is the first I minus 1 bits are your computer pseudorandom generator and bits. Take the first I minus 1 bits out of it. The next bit is random, and so are all the other bits. That's I minus 1. That's vi minus 1. Yes? So I minus 1 bits pseudorandom, the rest are random. Here's a funky way to generate that distribution, I claim. Okay? I generate the first I bits, not I minus 1, I bits to be pseudorandom. The rest are random. Okay, that's distribution 1. The other distribution is the first I minus 1 bits are pseudorandom. The ith bit is the opposite of the pseudorandom. It's not random. It's the complement of the pseudorandom. If I toss a coin and I sample from either di or di prime, now put the distribution, what you get is precisely this. Yes, because the first I bits are pseudorandom. First I minus 1 bits are pseudorandom. That's the way it is in both cases. In the ith bit, I either output yi with probability, yi is some bit, okay, with probability half, or yi complement with probability half. It doesn't matter. That's a random bit. Okay. Write down the conditional probabilities. I recommend that you do it. These are intuitions that you develop after writing down these equations, and then you say, aha, I shouldn't have written down these equations in the first place. But you won't know it until you write down the equation. Okay? So I recommend you do it. But I've done it so many times, it pains me to write it again. Okay, so that's that. So that suggests the following distinguisher. This is the following predictor, following next predictor. Okay? Here's what the predictor does. He flips a coin. He gets the first something a little bit off here, which means I lost here. This is wrong. Yes. So I have y1 up to yi minus 1. My goal is to predict yi. Yes? So y1 up to yi minus 1, very good. The ith bit, I'm going to plug in the coin here. Okay? The rest of the bits are random. So really, all the bits are random. Okay? That's what it is. And I say, what does the distinguisher output? Okay? If he outputs 1, I'll output one thing. If he outputs 0, if he outputs 1, that's sort of saying that, what is PR? So he outputs 1 with bigger probability if I give him the I pseudo-random bits, right? So if he outputs 1, I should take that as an indication that the next bit, the C bit, was actually pseudo-random, was actually the output of the pseudorandom generator. Yes, sir. And in which case I'll just say, here it is. This is the next bit of the pseudorandom generator. Take it. So work through the chain of arguments. So D outputs 1 with bigger probability if C was the correct answer. So if D outputs 1, I should output C. That's the correct answer. D outputs 0, I should output the opposite of C. Yeah, this is my next bit predictor. Now the question is, does this predictor actually work? How well does it predict the next bit, yi, given like 1 to yi? And one can show that this is large. This is essentially half plus how well the distinguisher does, which is epsilon over m, right? Because we did the hybrid argument, we said these guys differ by epsilon over m. So I'll claim that the predictor predicts the right next bit with probability half plus epsilon over m. Since epsilon is polynomial, 1 over polynomial, and m is polynomial, epsilon over m is 1 over polynomial, so that's pretty good. And that's again why, if m is 2 to the n, this won't work out very well, because a hybrid argument loses proportional to the number of bits. So you lose a lot if m is very large. Necessarily so. Okay, so now let's do this argument. So what do I want to argue? I want the probability that the predictor who gets y1 up to yi minus 1 outputs yi correctly is bigger than half plus epsilon over m. This is what I want. Yeah, this is what I want to show. But I don't have it, so let me try to sort of analyze this probability and conclude that. Okay. So what is the probability that the predictor when does the predictor output the right yi, the right answer? When C is equal to yi and the distinguisher outputs 1, he is correct. Okay? When C is equal to yi and the distinguisher outputs 1, the predictor outputs C, which is yi. Okay? So, probability that the distinguisher on whatever it is, YCU, yeah, outputs 1, conditioned on C equals yi, times the probability, this is base, yes, or just conditional probabilities, no better. Probability that C equals yi, plus the probability that D, or if C is the opposite of yi, and the distinguisher outputs 0, I will output the opposite of C, which is the opposite of yi, which is yi. Okay? So that's another event that I went. C is not yi, times the probability that C is not yi. This is just conditional probabilities. And these two are exhaustive, yes? Either C is equal to 1 bit or it's opposite. Good? So what is this? This is half. C is around a bit. And this is a half to. Yes? What is this? This probability, this thing in the middle. The probability that the distinguisher outputs 1 if C is yi, which distribution are we sampling from? So let me write this down. Pi minus 1, sorry, Pi prime is, this is all pseudorandom, and this is the complement of yi. Okay? So if C is equal to yi, I'm sampling from this distribution. Yes, the first I bits are pseudo-random, and the rest are random. Yeah? And the probability that D outputs 1 in this case is by definition PR. So it's PI times the half there. What happens if C is the opposite of yi? C is not y. Which of these three distributions am I sampling? Pi prime, Di prime, this distribution I prime. Rather, the probability that the distinguisher outputs 1 is Pi prime. But what I want is the output 0. So that's 1 minus Pi prime. 1 minus Pi prime times a half. Yes? So what is this? This is a half plus a half times Pi minus Pi prime. Yes? And what is that? Let's go back here and think about it for a second. Okay. So we know that Pi minus 1 minus Pi minus Pi minus 1 is at least epsilon over m. Yes? What is Pi minus 1? It's the average of these two. So Pi minus Pi plus Pi prime over 2 is bigger than epsilon over m, which implies that if you do the calculation, you get Pi minus Pi prime over 2 is bigger than epsilon over m, or rather this is bigger than 2 epsilon over m. Okay. Now, just arithmetic. Okay. Move things around. Okay. So this guy is large. So this guy is larger than half plus 1 half coming from here, 2 epsilon over m, which is half plus epsilon over m. Okay. So the predictor outputs the correct answer through this calculation with probability bigger than at least half plus epsilon over m, which is exactly what we want to show. Okay, let's start. End of story. Yes? Yes?
Can you explain why Pi minus Pi prime is greater than
Epsilon over m?
Yeah.
That's because that's because we started by the assumption that the distinguisher works, right? Which is saying that P0 minus Pm is bigger than epsilon.
So that works for one I between 0 and n, right?
Correct.
How does that mean that it works for this particular I?
No. This predictor, right? I only guarantee that this predictor works for some I. So the next bit unpredictability definition says that there is no I such that a predictor given the first I bits predicts the I plus 1 bit correctly. The opposite of that, to contradict that definition, all I need to show is some I. Remember what we are trying to show.
But that some I depends on the pseudorandom string. So for different pseudorandom strings, the I might be
It
different.
doesn't matter.
Really?
Doesn't matter. It's a probabilistic statement, right? I'm not saying, here is one I, which works for all pseudorandom strings. Think about it as this game. The predictor comes up with, the game is the predictor comes up with some I. Now he's given the I minus 1 bit prefix, and he predicts the ith bit correctly. Right? That's the game you want to come up with. I think I see what you're saying. It should be an averaging argument, essentially. Right? Yeah, that's right.
So it would get worse by another factor of n. At most.
Doesn't need to get worse by another factor of m. That's what Alex is saying. It's basically an averaging. You don't need to get worse by 1 over m. You need to do this a bit more carefully.
How do you prevent it from getting worse?
What should we think about it? You don't need to do epsilon over n squared. Okay. Offline. Do you see an immediate answer? So you don't have to, but let me. Since I depends on the distinguisher, really. It doesn't depend on the pseudorandom string. It's a, sorry? Don't see here.
An experiments are, they don't depend on the string at all.
Yeah, right. Depends on the distinguisher.
Yeah,
Doesn't depend on the string.
that's fine.
So, right, so good. So we define sort of m probability, m plus 1 probability distributions, right? So we're not talking about a particular string. We're talking about a random string generated as the output of pseudorandom. When you feed it n bits, you generate a distribution. Yes, so these are. Now what we're claiming is that this distinguisher says 1 with different probabilities if I feed it one distribution, like randomly choose a string from one distribution versus the other. Right? So once you fix the distinguisher, you fix an I, for which he says 1 with bigger probability on one over the other. And that I is the I. So there is one I for which.
Yeah, but it definitely does not depend on the string. It depends on the distinguisher, but now you're saying, do I feed it, the first I bits to be from the PRG, or the first, different I bits, but it's, yeah, there's
Yeah.
no problem.
Depends on D, but doesn't depend on the string itself. Good, excellent, beautiful. Okay, so, okay. Very good. Now I have 20 minutes to show you a construction of a pseudorandom generator. Let's give it a shot. Okay. So one-way permutation. So the next theorem is, so we argued about definitions. We didn't argue. I told you two definitions. They are both equivalent, right? And the important thing to kind of take away from here is the hybrid argument technique. And we'll do it again in this one. Okay. So how do you construct pseudorandom generators? So here's the, so I'm going to show you a construction from one-way permutations. Any one-way permutation. You give it to me, I'll give you a pseudorandom generator. That stretches by what? I don't care. Like n bits to some polynomial length. So F be a one-way permutation. Okay, so here's the construction, candidate construction. Okay, so pick a random seed. Well, okay, the input to the generator is a seed S, n-bit number. S, random n-bit number. You compute f of s, output it. Compute f of s, output it. Compute f of s, output it. And that's a sequence. Okay. Now, this is not pseudo-random. It's not even next block unpredictable. If I know this guy, I will predict all the other blocks. Yes. So this doesn't. This is not pseudo-random in any sense. You know what? Let me do a trick, which is actually quite confusing. But okay. So these I'll call them f squared, f cubed. It doesn't mean f of s squared. It means f of f of s. Okay. So here's the construction. I do exactly the same thing. I output this in the reverse order. Okay. I don't output f of s, f of s, and so forth, but I output it in the reverse order. Okay. What am I doing? Well, given this block, can you predict this block? This entire block, numbers, n-bit numbers. Can you? No, because this guy is the inverse of this guy. Yes? So it's like f of s is the inverse of f of s. Okay. You cannot predict this one. If I give you this and this, can you predict the next one? No, because this guy is the inverse of this guy, which is actually a random string. One-way permutations make sure that if I compute the function f on a random n-bit number, I get a random n-bit number. So it doesn't matter actually. Yeah. So there is some unpredictability, something going on. Is it a pseudorandom generator? No. Why not?
Well, we have that equivalent definition for number 1, which said it doesn't matter what bits you have.
True. That's one way to kind of get out of this situation. Okay. That's fine. But the fundamental thing here is that one-way permutations don't guarantee the randomness of any single bit. Yes. Here is a one-way permutation. It applies another one-way permutation on the first n minus 1 bits, and outputs the last bit by itself. That's a one-bit permutation, yes? If you apply this function again and again and again, the last bit remains the same. So you don't get it. So is it? Yeah. Next, block unpredictability doesn't tell you anything. Yeah, that's all right. Good. So this suggests something, right? I mean, I don't want to deal with blocks because blocks say, well, I can't predict the entire string with probability bigger than 1 over polynomial. But that doesn't say anything about a single bit. But there is an object that tells us something about a single bit, yes? That is hardcode predicates. That is the right object. It's the right thing to use. Hardcode predicates. If you know what it is, I've told you enough about it in the last 2 lectures. That's what it is. You can compute B, a predicate, a bit, easily from X, but given f of X, it's hard to predict, even a little bit. B of X. That's what I'm going to do. Here's the construction. Okay, I'm going to expand I'm really going to expand big time. Okay, so any polynomial, I'll expand to from n bits to p of n bits. That's the generator. Here's the construction. On input S, n bit string. My algorithm is going to keep an internal state, never going to output it. Okay, and then I'm going to output bits. So how does it? This is by the way, I didn't write it down. This is the construction of Drum and Mikali from the early 80s. F of S, very good. Right? What am I going to do with S? I have a one-way permutation. I have a number. Just apply the thing. I'm not going to output F of S. Instead, I'm going to output B of S. Okay? So B of S is truly random. Yes, I mean it's truly random. What am I going to do next? 1 bit is no good. Yes, n bits, 1 bit, no good. I apply the function again. So I did do the same thing that I did before, except I never output the thing on the left. F of S, F of S, blah, blah, blah. Every time, what I do is I output the hardcode bits. So this time, I output the hardcode bit of S. Here I output the hardcode bit of F of S. And here I output the hardcode bit of F of S. That's what I do. This is the output. That is never output. It's discarded once the computation is finished. Yes?
Why should this be in reverse order then?
This reverse order is a trope. Okay, it's it makes. Let me put it this way. I want to argue pseudorandomness of this. Okay, you have 2 definitions. You can use either one. Doesn't matter because they're equivalent. Right? Which one are you going to use? Well, you start thinking about it, writing down the proof. You realize that the next bit unpredictability definition is a nicer one to argue things about. Right? The next bit unpredictability definition is sensitive to which order you do things. So in one order you might be able to prove things, in the other order you may not be able to prove things. The fact that you may not be able to prove things doesn't mean it's not pseudorandom, it's just the limitation of it. So just it's a fact that comes together with your use of this thing. Just think about it that way. Really, I mean if a string is pseudorandom 1, 2, 3, 4, 5 bits, it should be pseudorandom 5, 4, 3, 2, 1 bits. Right? I mean it doesn't really matter. Very good question. It's confusing. Yeah? It's confusing. Okay, so compute this. Why am I doing it? I will prove it. So we'll prove that this guy is pseudorandom. Proof on the board. Good. Excellent. Let us do it. All right. So how do I want to prove this? Right? Again, contrapositive. Okay. Suppose this sequence is not pseudorandom. Yes. Which means that there is a next bit predictor. Which means that there exists an I such that there exists an algorithm P. Right. Such that the probability that when you feed the predictor with P1 up to Pi minus 1, it predicts Pi is bigger than half plus epsilon. Or some half plus 1 or Q. Yes? So we have this. Why do we have this? Yes.
Sorry, FP of S, how is P defined there?
How is P defined? P is P of n.
Okay.
P is, yeah, sorry. Yeah.
Okay.
So the output is supposed to be P of n bits. Here are the P of n bits.
Okay.
Good question. Thanks.
That makes sense.
Okay. So I want to argue that this string is pseudorandom. Yes. This distribution produces pseudorandom. Suppose it isn't, which means there is an explicit result, which means there exists an I and the algorithm thread such that given I minus 1 bits, it outputs BI with probability bigger than half plus 1 over 4. Now I want to do what? I want to use this to break the one-way permutation. Right? What I will do is I will use this to construct an algorithm that predicts the hardcore bit. Given f of something, I will predict the hardcore bit of that something. Okay. So what I want eventually is an algorithm, hardcore bit predictor, such that if I feed it f of x for a random x, the probability that it outputs b of x is bigger than half plus 1 over p prime of n, or some other form of it. Right? Once I have this, I already broke the one-wayness. I didn't directly break the one-wayness, but put this together with the fact that this is a hardcore predicate, not Goldreich-Levin necessarily. To put this together with the definition of the hardcore predicate, I broke the one-way permutation. Yes? So how do I go from here to here? Okay. Very interesting. What do I want this guy to do? I want him to output b of some x. Yes? What x? An x for which I have f of x. Yes? So I want to set things up the right way here. So let's write this down explicitly. Okay, so what is b1 up to bi minus 1? It's b applied to p minus 1 evaluations of some some s, yes, comma, b applied to p minus 2 evaluations on some s, comma, up to b applied to 1 p minus 1, p minus I plus 1 evaluations on some s. Right? So that's what this is. And bi is b applied to yes, explicitly wrote it down, what these bits are. So I have to somehow generate these bits, b1 up to bi minus 1, from the correct distribution, this kind of distribution, and yet I should not know what bi is. Because if I knew what bi is, what do I need the distinguisher? What do I need the predictor for? Throw it away. Yeah? He has to give me something good, meaningful. How do I set it? Okay, so I'm going to do it. I will rename a fp minus I of s as x. Call it x. Okay? I can call it whatever I want. Let me call it x. What is the distribution of fp minus I of s? Just by itself. Okay, I pick a random s. I compute the one-way permutation p minus I times. What is the distribution of the resulting string? The permutation. The one-to-one onto function. Yes? That's the probability that you will get any particular string. Another way to say it is that this distribution is random. If I take a random input, apply a permutation, apply a one-to-one onto function to it, you get a random string. If you write another time, you still get a random string. Another time, you still get a random string. So in other words, this guy, if you look at the distribution of this guy, just by itself, marginal distribution, is a random string x. Yes? So if I rename things this way, what the adversary gives me is b of x, which is what I want. Yes? Rename. But he won't give me b of x until I give him the right numbers before. I mean, he's not for charity, yes? I mean, he gets things and then gives things. Okay? So, but what is b of, what is fp minus I plus 1 of s? F applied p minus I plus 1 times on s is the same as f applied to p minus I times. So this is equal to f x. Yeah. So on and so forth, and this is equal to, well, I have to compute now. I minus 1, probably. Yes? Computing in the room. Now the magic here is that what is the game I'm playing? I have f of x, and I'm trying to predict b of x. If I have f of x, I can compute b of f of x, which is this bit that I have to feed to him. I can compute b of f of x. Well, if I have f of x, I can compute all these guys. I can compute b of all these guys. I can feed it all to the distinguisher. I can feed it all to the predictor. I have his input. I can produce his input. And then he says, you know, thank you very much. Here it is for free. You get b of x, and then I win immediately. Does it make sense what I'm saying? This is the argument where you wouldn't be able to carry it through if you did the opposite. Right? I used very crucially the fact that what he predicts, the things that I'm supposed to feed to him are things I can compute starting from this way forward. If you did the opposite, I would have had to compute the inverse of that to recreate all these bits. I won't be able to do it. Right? So it's very important, this order, for this proof. Yeah? Good? Makes sense. This is the pseudorandom. This is why this guy is a pseudorandom generator. Yeah? Okay. How do you instantiate it? Take any one-way permutation, take any hardcore bit for that one-way permutation, you're good. For example, the discrete log and the most significant bit hardcore bit, or any one-way permutation and the Goldbeck 11 hardcore bit. It all works. Okay? This is a generic recipe to get a pseudorandom generator from any one-way permutation. There are several things that you can get from the proofs that we did today. Like for example, remember the next bit unpredictability and pseudorandomness proof? That would give you many statements. I'm not going to show this construction. Here is a statement you can show. Suppose you have a pseudorandom generator that stretches n bits to n plus 1 bits. Okay? It's not a very useful one. I pay maybe $10 for it. Okay? But I claim that I can use this pseudorandom generator, once I buy it, to stretch to any number of bits. It doesn't matter if I stretch by 1 bit. If I produce 1 pseudorandom bit, or 100 pseudorandom bits, or polynomially many pseudorandom bits, you can turn one to the other. And how do you do it? You know the construction we just saw from one-way permutations to generators? You do exactly the same construction, and you will get the answer. So let me just show you write the construction and proof for you. It's an exercise. Okay, so you have a pseudorandom generator G that stretches by 1 bit. Okay, so S is a seed, and bits apply G of S. So you get n plus 1. Yes? That's all it's going to give me. It's going to give me n plus 1 bits. That's it. End of story. What I do is I output the n plus 1 bit. Just the n plus 1 bit, not the whole thing. I'm going to keep the rest to myself. Then I'm going to rename S to G of S. Rather, this is my new seed. G of S is my new seed. Repeat. New seed. Apply it once more. G of S in this case that again stretches to n plus 1 bits. Output the last bit. Keep that as a C. Now you do G of, G of, G of. Good. Yes? One way to get the construction we described from one-way permutation to pseudorandom generator is to take a simple pseudorandom generator from one-way permutation that stretches n bits to n plus 1 bits and apply this construction. You will get something that's identical to what we described. So what is a simple pseudorandom generator that stretches n bits to n plus 1 bits? Here's the generator. It takes n bits. Okay. It outputs f of s concatenated with b of s. F of s is truly random. There's no way you're going to next bit predict, do any funny things. And given f of s, b of s, you cannot predict at all. So there you have it. You have n plus 1 pseudorandom. You take that construction and you apply this range extension, you get the construction we showed you. We saw a couple minutes ago, 10 minutes ago. Okay? So we can do amazing things with these. Okay? So now I say, why one-way permutations? Why not one-way functions? Yes?
Sorry, just to clarify.
Yes.
When you said S equals G of S, you mean set it to the first and just...
Yes. Good. Very good. Very good. 1, 2 of times. Exactly. Thank you. Yeah, I mean, otherwise.
Sorry, can you just like keep the board behind it visible?
Yeah. Sure. Of course. Yeah. So this construction does not work if I start from a one-way function. You should think about why not. But with one-way functions, the following thing can happen. The first time I apply a one-way function, let's say n bits to n bits, it shrinks the domain by half, let's say. If you apply it again, it shrinks by another half. If you apply it again, these kind of things can happen. So n applications, successive applications of a one-way function can basically map to 0. So I recommend you to construct such a counterexample of a one-way function. F is a one-way function, but if you apply it sort of n times to itself, f of f, you'll get 0. Okay? So this doesn't work. This construction by itself doesn't work. However, you can. There's another construction that does work. It takes any one-way function and constructs a pseudorandom generator out of it, and this is the Hastad so-called Hill construction. Okay? And we have notes, we have papers, notes on the web. It's a very complex, very sophisticated construction. People have, there are multiple conference best paper awards just to simplify this construction down to something nice and understandable. Okay? Regardless, for those of you brave enough, I recommend that you look at it. It's very illustrative. It would be nice if these two guys were equivalent, right? I mean, if there exists a one-way function, if and only if there exists a PRG, that would be very nice. But is that really the case? Well, that's up to you to figure out. That's why it's a dotted arrow. It's not. And then we'll continue.